All right, it's 2 o'clock. So you, if you're turning in a mini exam, I'll take that now. And if you did the bonus question, I'll take that. We'll do 2 separate piles. Just make sure your name is on both, please. Mini exam, mini exam. Mini exam. These your mini or bonus? Bonus, 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 mini, bonus. Okay, this is mini exam, bonus. Bonus and mini. Yeah, do you have it? How is it?
I got it together at the end of it.
Yeah, just tear it off and put your name on it. Okay, bonus and then mini.
We're trying to create a function of C, right?
Mini. Okay, thank you.
You see at the very top. That's a rotate 3 times.
Okay, bonus and mini. All right. Anybody else? Okay. All right, so I've been asked to discuss the bonus question. So we can talk about that for a moment. I don't remember the problem. We had our silo, it was 20-foot diameter, right? 90 foot tall. And we had a 180-pound man with a 20 pounds paint that's leaking, so that when he gets to the top, it was 20 at the bottom, and then when he got to the top, how much was it? 16 pounds. So what it basically comes down to is you're trying to find, we already had the parametric representation of the curve. That doesn't change. The only thing that changes is the actual field. So our field here would still be a downward pointing vector, but instead of it just being the combined weight of the man and the paint, this is going to be, it'll include a variable because this is changing with time. So remember we had set our t between 0 and 6 pi. Is this okay? I'm not doing the whole like setup. It's okay, just talk about it this way. We may as well do the curve. The curve was r of t was 20 sine t, 20 cosine t. And then this was that part that we had talked about trying to figure out this piece to make it be 90 at the end. Yeah, so we did like 90 times t over 6 pi, something like that. And then we reduced it and cleaned it up. So all of this stays the same. That'll take us up the silo. But this part right here is going to change. So what did y'all do here? Anyone want to share how they did that part?
So I did combined.
Uh-huh.
Combined with this, I got 200 pounds.
Okay.
And then at the end, I got, so I basically got 2 points. The starting point and the ending point, which gave me a line, like on the slope of the line.
Oh, okay, like a slope. You could do it that way. Yeah.
And then plug it in the slope to an equation that it gives t.
Yeah. The main thing is you want it to start out, when t is 0, you want his weight to be 200, right, combined? And at the end of 6 pi, you want it to be what? 196. So you want it to lose 4 pounds as t goes from 0 to 6 pi. So you could do something like this. You could do 200, right, is what he starts at, and then you subtract from that. It's very similar to this. You know, you want it to You want to lose a total of 4 pounds, just like you wanted to get to a height of 90, right? And you want to do this as t goes from 0 to 6 pi. So at t equals 0, you will have 200-pound man. When t gets to 6 pi, you will have taken away 4. So this is kind of like you were saying, the slope comes from this right here. Does that help?
Yeah.
Okay.
I didn't get enough time to look at it, but I wanted to see
Yeah.
how it was.
Yeah, so I mean, what winds up happening is at the end of it, you're gonna dot these things, right? And when you dot them, you know, it's gonna just be a little bit different integral, but it's pretty clean still. Okay, we are moving on to chapter 13, section 3. Oh, and I wanted to show you something. There is a summary of the formulas that we picked up just in chapter 13, section 2. So this is just the formulas that we developed last class. We had the idea of this notation here, the integral over a curve C of a function of a scalar function of 2 variables with respect to S. This was this was the area of that curtain below the surface, right? That's what this is. And this is the formula for it. Then we had that same sort of idea, but with respect to X, then with respect to Y. And then after that, we introduced this idea that anytime we see something like this is the notation we would use. And then we talked about what happens when you change the direction. If you change the direction of the curve, then you add the negative. Pardon? If it's dx, right, or dy. If it was with respect to s, then it didn't change, right? That's this last one. And then we did the same idea, but now a curve in 3-dimensional space, a function of 3 variables with respect to arc length. And when we went to the 3 variables, we started using a different notation. We started using this r of t, this vector function. And then we rewrote this as the magnitude of the derivative. So we had that, then we had that same thing with respect to just x, with respect to just y, with respect to just z. So we had 3 new integrals. Then we had notation again. And then we started talking about the line integral of a vector field along a curve. So this was where we had the idea of work. And we went through and said, here's the notation we use. Here's what it was when we looked at it. You know what? I think I'm missing ds here. I need to go back and check that. I believe I'm missing my ds. But this is the formula we wound up using right here. And then we said that this was really important. We said that this right here can also be looked at using this formula. So there's a way to make it go from like vector stuff to scalar stuff. And yeah, that's it. Those were just the formulas for 13.2. So I don't know if you've noticed, but in Canvas, I have a formula summary that you can bring to the final. And it's basically a summary of chapter 13. I think it's 16 pages long. It's a lot of formulas. We've got a few of them here. We've got like 5 pages of the 16 so far. Okay, so we have a lot of stuff still coming. Yeah. All right. 13.3. The fundamental theorem of line integrals. The fundamental theorem of line integrals. So in Cal 2, you learn about the fundamental theorem of calculus, right? And there's a couple of versions of the fundamental theorem of calculus. But the evaluation theorem from Cal 2 says basically that if you have this, right, then this is capital F of B minus capital F of A. Right, that's our fundamental theorem. That's one of the 2 versions of it. This is called the evaluation theorem or version. And this says, again, that if we have some function, f, scalar function here, we can find the area. But to find the area underneath this, we need to find the antiderivative of that, right? And then evaluate it at the 2 endpoints, which is amazing that this works. But this is the fundamental theorem. So I'm going to rewrite the fundamental theorem here, but I'm going to rewrite it in slightly different notation. I'm going to replace capital F with little f. And then what would this have to be changed to then? Yeah, so remember, capital F is the antiderivative of that, right? So if I replace this with little f, then this has to be f prime. Agreed? That would be the same formula. Saying, hey, look, if you were looking at the derivative of a function and you want to know the area underneath that curve, that you would just need to find the antiderivative of it. I'm just writing that, it's the same thing, right? Okay. Now we move on to this very important theorem, the fundamental theorem of line integrals, and it's going to look a lot like that. So it says if C is a smooth curve, okay, so remember we have a curve, and right now we are not talking about whether or not our curve is in 2 or 3 dimensional space. Just let that be a smooth curve where you have a vector function that draws it. You have restrictions on t, right, which will draw your curve. And as long as f is differentiable and it's either got 2 or 3 variables in it, such that the what? The gradient of that scalar function is continuous on C, meaning when we take the gradient, it's defined, it makes sense on the curve. Then we have this result. Okay, so do you see the similarities between these two formulas? You have, the integral over something. There it's a to b. For us, it's a curve. The gradient is in some way the derivative of a function, isn't it? The gradient of a scalar function is a type of derivative, but it spits out a vector, right? So this is a vector function, but the antiderivative of this is kind of just the original function little f, isn't it? And that's kind of what's happening here. This is almost like the gradient of little f, right? If we want to know what this is equal to, it's equal to the antiderivative of that minus evaluate the 2 endpoints, right? So that's what this is saying. It's saying this will be equal to the original scalar function evaluated here minus the original scalar function evaluated here. Now R of B and R of A are the 2 endpoints of your curve. So you have a curve. We're trying to evaluate the line integral over that curve. This theorem says that if you can somehow recover the little f that this came from, then all you have to do is evaluate it here and here and subtract the 2 and you get the answer. Which means that this is a conservative vector field, right? This only works if you have a conservative vector field, because by definition, a vector field is called conservative if it is the gradient of a scalar function. You have to go back and look at your definitions. So that's what this is all saying. And what's really kind of amazing about this is that this is saying that the line integral on any 2 paths that connect the same 2 endpoints are always equal as long as the vector field is conservative. So do you remember last class we did a problem where we had, I don't remember exactly the points, but we had like a straight line and we called that like C, and then we had another one was like a parabola opening sideways, we called it C tilde, and then we evaluated a line integral along both C and C tilde, and we compared them. We said, do they give us the same answer? And I think I didn't do it. I said, do y'all believe that it will be different answers? You said yes. So we concluded that from that last class that in general, if you do line integrals, your path matters, okay? If you start at the same point and the same point, the path is going to have an impact on that answer. This is saying that if this in here, right, if what you're doing the line integral of, this right here, this vector field, if that is a conservative vector field, that the path isn't going to matter. Because at the end of the day, your answer is just the original scalar function evaluated at the 2 endpoints. So that means all that really matters is what's happening there and what's happening there. Okay? But we have to have a conservative vector field for this to work. That's why we like conservative vector fields. So let's do an example. let f, the scalar function, f of xy be equal to x squared plus y squared, and c be given by this vector function t sine t, t cosine t, and our interval is t is between 0 and pi. We want to find this, right? We want to find this. Well, the theorem says that this should be equal to little f evaluated at r of b minus little f evaluated at r of a. Do we know little f? We do, right? We know what little f is here. So all we need to do is evaluate this function where? At r of b. What's r of b? So for us here, I'm going to move this down here. R of b is really r of what value? What's b for us? B is pi, okay? And then minus our scalar function evaluated at r of a, which is 0. Now, do we know what r is? R is our curve, right? Do we know our curve's value at pi? Sure, we can plug pi into this, right? So this is going to give us f of, let's see, what happens when we plug in pi? We get a vector, don't we? Yeah. Okay, we get the vector pi sine of pi. But sine of pi is 0. So that's going to give us 0? Yeah. And then we have pi cosine of pi. What's cosine of pi? -1. So negative pi there. That's a vector. And then minus r of 0. What is r of 0? So we get the vector 0, 0. Now, I told you a few classes ago that this notation is weird because you're trying to plug a vector into a scalar function. But all this really means is this is x and this is y. So you're going to go into your scalar function right here, replacing x with 0 and then with negative pi, and then you subtract 0 and 0. Make sense? So we get, let's see. I'm not thinking right now. What happens? Pi squared, right? That's what happens when you plug that into f. You get 0 squared plus pi squared, negative pi squared. And then minus, when you plug 0 and 0 into that, you just get 0. So your answer is pi squared. All right? If you're looking at the line integral of a conservative vector field, you just have to be able to evaluate the original function, the scalar function that created this conservative vector field, and just evaluate the two endpoints. All right? Nice? Now, what would we have had to have done had this, if we didn't have this theorem? We're not going to go through the whole thing, but what would be the setup for this if we didn't have this theorem? Yeah, so we would start out by finding the gradient of that. What is the gradient of f? Gradient of f would be equal to partial of that with respect to x, partial with respect to y. So it's a two-dimensional vector, right? And so this would become line integral over c of 2x, 2y, dotted with, now what is this? That's r prime of t, right? R prime of t dt. So what is r prime? What's the derivative of r? Yeah, so we have to do the derivative of this first, which would be like sine t plus t cosine t. Then we'd have to take derivative of that, which would be cosine t minus t sine t dt, right? And then this right here, we're not done. We have to get everything to t. So what would we replace x with? Whatever x is right here. So this would now become, and I'm going to change it over to 0 to pi. And we would be doing 2t sine t, 2t cosine t, and then dotted with that, right? Yeah. And then we dot product. We'd have a bunch of t sine t's. I see a bunch of integration by parts here. I see this not being fun. and at the end of it all, we should get pi squared. A lot more work, yes?
Yes.
Okay. So if we have the scalar function, right, and we're asked to find this, then we have a quick way of doing it. All right. So just some more results of this. So path independence. First, we need to understand what a closed curve is. I think a closed curve is pretty easy to understand. It's a curve that starts and ends at the same place. Okay? Closed path has the same initial and terminal points. So we have a closed curve here. This theorem says that the line integral of f over some curve c, so this is like our work integral, is path independent if and only if the work is 0 for every closed curve or path in D. So this theorem actually is not very useful to us, because what it says is that in order to show that the path doesn't matter on a closed curve, to show it doesn't matter, that it does, so if I start here, right, or if I do a different curve or a different curve, to show that the paths don't matter on a closed curve, I would have to do it, I'd have to show that it equals 0 for every single possible curve you could ever draw. And that would be impossible to do because you don't have the time for that, right? And I think we saw this with like limits. You couldn't do the limits because you can't come in from every direction. All right? But if this is conservative, right? If that's conservative, if that is the gradient of some scalar function, then what can you tell me about the value on any closed curve? Same, but more than the same, it's going to be 0, right? Because if you're doing this, if you're going to do this, and I tell you that this curve is closed, right? Then the starting and ending point is the same. Then when you use the fundamental theorem of line integrals, you're going to be subtracting the same thing minus itself, right? Because your starting and end points are the same. So that will always give you a value of 0. So this is what this is saying right here. So line integrals on closed paths of conservative vector fields are always path independent. Huh? As long as it's closed and it's conservative vector field, then the path doesn't matter. You're always going to get the same result. You're always going to get 0.
And so that only, and then if it's just a regular vector, if it's just a regular vector field, then that does matter.
If it's non-conservative, you can't conclude that. That's correct.
Okay.
Okay, now a little bit more about curves. We have an easy way to check whether or not, if this was something from a few classes ago. We said, if I give you a vector field, can you tell me whether or not it's conservative or not? And I said there will be an easy way to check later. We weren't ready for it. So it's time for that now. Here's how we check. If someone hands you a vector field and asks you, is it conservative? Here's how you check. But before we can use the theorem, we have to have a couple of little things established here. This right here is what we call a simply connected region. Right? Do you agree that, does that look simple to you? Without getting into too much of the topology of this, the idea of a simply connected region is that if you pick, look at this region here, if you pick any little path in here, okay, so imagine I pick a path. Imagine this is like some sort of rubber band or something, okay, some closed path. If I shrink that path down to a point, as I'm shrinking it, this rubber band always stays inside the region. And that holds for any rubber band I ever draw. So if I do another rubber band that does this, okay, if I take that and start shrinking it down to a point, as I shrink it, the rubber band always stays inside the region, right? This one is not simply connected because, well, I can have this rubber band here. That's not a problem, right? I shrink that down, Everything's going to stay inside. But if I draw this rubber band, I can't shrink that down, because as I start to shrink it down, it starts to hit the boundary of the region, right? And so if I try and shrink it to a point, I've got to somehow push that rubber band through that open spot, and I'm no longer inside the region. So this is not simply connected, this is simply connected. Understand? Yeah. Okay, so this theorem says that let F be some vector field, okay? Two-dimensional, not three-dimensional, a two-dimensional vector field. Let F be some vector field on a simply connected region. So we have to have that. In other words, we're only talking about a field on one of those nice regions up there. Suppose that these component functions, P and Q, have continuous first-order partial derivatives, meaning we can take the partial derivative of this, partial derivative of that, and those answers, those partials, make sense. They're defined within the region. Then, if the partial of P with respect to Y, that means the partial of this one with respect to Y, if that equals the partial of Q with respect to X, then that was a conservative vector field. That's the check right there. That's it. Those two partials have to be equal. Now, I'm not going to prove this. When we get to the next section, or when we get to Green's theorem, I might talk about this a little more. But for now, we're just going to take this on faith, all right? Super quick, easy check to see if a vector field is conservative in two-dimensional vector fields. So I'll write that over here. So we have partial P with respect to Y has to be equal to partial Q with respect to X. All right, so take a look at this. Is this a conservative vector field? Well, they don't give us a region, do they? But the domain of this vector field is all real numbers. You don't have any division by zero, you don't have any square roots, you don't have any weird trig functions where you have domain problems, right? It's basically polynomials. So the domain of this thing is everything. And so any region you ever pick is going to be simply connected. You all buy that? Okay, so what's our check? Well, we have to do this. That's P, and that's Q. Okay, we'll just go around the room again. Did y'all like that? You did, right? I think everyone in the class emailed me after class and told me how much they enjoyed that. All right. Go ahead. You get to start. This table will start, but I'll start with you. So just tell me what this is.
We could take the partial of P in terms of Y.
Okay, so what is the partial of P with respect to Y?
That's 2x.
2x, okay. And then the question is that equal to the partial of Q with respect to X, which is 2x? Yes. Right? That's partial P with respect to X, partial P with respect to Y, partial Q with respect to X. Check. This is a conservative vector field. That's it. There's nothing else. Right? So let me see if, yeah, okay, we'll leave it at that. Now, recall from 13.1 that by saying that F is a conservative vector field means that there exists some scalar function little f such that when we take the gradient of the little f, we get the vector field. In such a case, the little f is called the potential function for the field f. We now talk about how we go about finding it. And what we're going to use is something called partial integration. Not integration, partial integration. Just like derivative, partial derivative, same idea. We're going backwards now. So what we'd like to do here, let's do this example first, because this, well, is that the same one? No, it's not. Let's do this one. Okay, so everyone agrees that this f is conservative, right? Yes, everyone agrees f is conservative. That means, thus, that means there exists there exists a little f such that f, our field, is equal to the gradient of little f, right? So by saying a vector field is conservative means that there exists some scalar function such that when I take the gradient of that scalar function, it's going to give me that field. We need to find it now, all right? Let's find little f. So here's what I know. We know that the gradient of f is what? What is the gradient of f? In this problem, what's the gradient of f? It's that, right? It's that vector field. That's what it is. 3x plus 3 plus 2xy, and then x squared minus 3y squared. All right? That's what it is. Now, do you remember when we took the gradient of a scalar function, like we did that example a second ago? Remember this example? And when I was showing you the longer way of doing this that would have sucked for us, we found that the gradient was 2x, 2y, right? Yeah. Right, we did this. So this first component is the partial of that with respect to x, and the second one is the partial of that with respect to y, right? So from this information, here's what I know. I know that this is the partial of little f with respect to x, right? So I know that the partial of the scalar function I'm looking for with respect to x must be 3 plus 2xy. Follow? Yeah. I'm just focusing my attention on that. I also have that information, but I'm not going to use it yet. Just this, I know this is true. And remember, we're trying to find little f, right? So now here comes the partial integration. I'm now going to take that equation. I'm going to integrate the left side with respect to x, and I'm going to integrate the right side with respect to x. Now I'm doing it with respect to x because this was the partial with respect to x, so if I integrate with respect to x, that should take me right back to where it came from, which is what? What's the antiderivative of little f with respect to x with respect to x? Just f, little f, right? Which is what we're trying to find. So here's what I know. Little f should be equal to this antiderivative. Now the antiderivative of this, you're treating x as a variable. That means y is being held as a constant. So what would the antiderivative of 3 be? 3x, okay? Plus, now the antiderivative of this with respect to x, x squared y. But something always happens when we do an antiderivative of, well, an indefinite integral, right? We don't have limits of integration here. We always have something here, right? Plus c. Okay. But we have to be real careful with this because it can be more than just a constant. It can be more than just a constant. Let me see if I can, I'm not done, but let me put something up here. If I put here plus 4, do you all agree that if I take the partial of this with respect to x, I'm going to get this, right? And so yeah, I do need to say plus a constant. But what if it was 4y? It would still be this, wouldn't it? Wouldn't it? Because I'm treating y like a constant. So this idea of partial integration says that when you get to this step where you want to say plus c, it's actually not plus c, it's plus any constant, but also it could have y's in it, right? Even if, what if it was sine y here? Like sine of y. It would still give you that if you took the partial with respect to x, right? So I need to say it can be basically anything that has just y's in it. So I'm going to say any function of y. This is now acting like my constant of integration. But the key here is that this function right here can only have y's and constants in it. That's all it can have. So that when I take the derivative of this, it will go away. It will vanish. I know that that has no x's in it. Understand? Okay, so that's what I know about little f right now. I know, I'm trying to find little f. I know so far it's this plus something that has possibly y's and numbers by themselves. So what should we do next then?
Do y and see the partial, integrate the partial of y.
So you want to like do this and do the same sort of thing and go backwards?
Yeah.
Do y'all see we could do that? We could say, okay, just same logic here. This is the partial of f with respect to y. But I'm going to go a little bit different, okay? Just a little bit different. We could do that, but just follow me through here. Here's where we are, right? All we really need to know is what that is. If I know what that is, we're done. So what I'm going to do is take this, and I'm going to take the partial of it with respect to y. Okay, take the partial with respect to y. Let's see what happens. Nothing? X squared plus the derivative of this with respect to y, right? I'm going to write that as g subscript y. I could go g prime y, but I'm just going to go g subscript y. This has to match what? That, doesn't it? Because isn't this the partial of f with respect to y? This has to match this. You're getting that or not?
Yeah.
Okay? So I know what the partial of g with respect to y is, don't I?
Yes, it's minus.
It's minus 3y squared. So from that, I'm going to continue over here. Therefore, I'll use my 3 dots for therefore. Therefore, we have x squared minus 3y squared must equal x squared plus the partial g with respect to y. And that means that negative 3y squared equals the partial g with respect to y. But that's not what I wanted. I didn't want to know what the partial g with respect to y was. I wanted to know what g was. So how am I going to get back to g if I have this? Integrate it with respect to y. Okay? So I'm going to integrate the left side with respect to y. And I'm going to integrate the right side with respect to y. This will, well, this right here on the right side will take me back to g, right? Or g of y if you'd like. And then this, the antiderivative there is what? Negative y cubed plus, now it can be any constant. Okay, plus any constant. Because we already knew that g couldn't have x's in it, right? So when I get to the point where I go back, I say, okay, negative y cubed. Now, it can't have x's. I already knew that. So it could have constants, though, right? So we're there. We are there. We have what g of y is, and I'm just going to go replace it back in there. So here's our final answer. F, our little scalar function, is 3x plus x squared y minus y cubed plus any constant. Check for yourself that if you take the gradient of this, you will get that. So is the potential function unique? Is there only one? Well, it's a family, isn't it? It's a family. So if you were forced to just pick one of them, I would just let C be 0. And there you go. You've got a potential function. Right? Okay. So what do we have? Today we have so far with this that line integrals over curve C, or work, right? Don't over a curve C, is just the, if you've got a conservative vector field, it's just the potential function evaluated at the two endpoints. We also know that if you try and calculate the work along a closed curve, it's always 0 if your vector field is conservative. We know that if someone gives us a two-dimensional vector field, we can check to see if it's conservative. And if it is conservative, we have a method of actually finding the potential function using partial integration. So that's kind of everything encapsulated up to this point. So now we'll do another one. All right, so we'll continue going around the room here. You're out. Okay, so you want to start? One of you want to start this? Tell me. Just tell me what. I'm just going to do what you tell me. Whatever. I'm just a puppet up here. How are you going to answer the first question? Is this conservative? You have a question? Yes.
So, like, can you describe the potential function?
Describe it?
Yeah.
In this case, it's a surface, and the vector field that you get when you take the gradient is all those vectors that show where the ball's going to roll if you put it on any point on the surface. Are you trying to figure out like the connection between the field and the potential function? Yeah, so it's like if someone were to give you a vector field in two-dimensional space, right? You got all these vectors everywhere, right? If this is conservative, then there's a surface that goes with this where if I drop a ball right here, it's going to want to go in a certain direction. And if you look at that from the top, that corresponds to one of these vectors. So this is little f, and this is just the field in two-dimensional space. So the potential function is the surface that corresponds to that vector field. If this is not conservative, you don't have a surface that it corresponds to. So that would be like a surface you can't draw because the way this behaves, there's no surface that corresponds to it. Like there's ways to draw vector fields where the shit going on in here can't match up with any physical surface. There's too much random jumps and things like that. Does that kind of help a little bit? Okay. How are you going to answer the first question? Yeah, so we're going to use this, right? Okay, so you go ahead and let's do this check. We're going to be checking is the partial of p with respect to y equal to the partial of q with respect to x. Which one is p? The left one. So this one is p, and then this one right here is q, right? So what is the partial p with respect to x? To y? To y? Sorry, yes, you're right, 2y. Okay, 2y, 2x, 2x. I know, okay. I should just listen to you. I'm supposed to listen to you. 2x, keep going. Okay, so just that, and then you were asking, is that equal to 2x? And it is, right? So it's conservative. It's not always 2x. The two problems I've shown you have both been 2x. It's not always that.
Too late, I
All
already
right.
did that.
So now what? You're off the hook. So now what? It's conservative, right? So it says, if so, find the potential function. So how are we going to find the potential function? Find what?
The partial integral of these components.
So we have to do partial integration, right? So what's the first equation we set up? Or you know what to set up? No? Okay. It's all right if you don't. We only did one example. So what we know is that this is conservative, which means this right here is the gradient of some scalar function. We know that because of this check. We know that this is equal to that, right? And by definition, that means that this is the partial of our scalar function with respect to x, and this is the partial of our scalar function with respect to y. Okay? So when we do this, we always start out, well, you can start with either one of these. It doesn't matter about. Let's start with this one, and let's just write this down as an equation. We know that the partial of little f with respect to x must be that first component, right? And now we want to go from here to little f. So what will we do to go from here to little f? We have the partial of f with respect to x, so to undo that, integral, right? With respect to what? To x, right? So we want to do this with respect to x, and then we want to do the same thing on the other side. All right. Who wants to volunteer this next step?
Like volunteers or something?
Oh, just tell me what the next line is going to be.
Oh, in that case, the next line is going to be f equals.
F equals,
that.
f equals, and then you want to give me the antiderivative of that?
And you do it with respect to x in this case on the other line. So you're going to have x
Okay.
plus fx squared y.
Good.
Then the derivative of the natural.
Yeah, so that's either a formula that you remember or you, yeah,
X ln x minus 1.
minus x, close. X ln x minus x. You know what? I hate to do this. Okay. Yeah, she called me the other day in the middle of class, and I forgot what she wanted to know. It was something ridiculous, like, you know, where's the cotton balls or something like that. I'm like, don't call me for that. Don't call me if there's an emergency. All right. So keep going. Oh, this right here. Formula, or you just got it memorized at some point. I think we're kind of to that point now. You just want to kind of burn that one in. Like if you're going to be doing more math, like you're going to integrate natural log enough that you should just have this one in there. All right. Okay. And then very important. What's our next piece?
You need to add the gy.
That's right. We need some function of y here, for the same reason as before. Right? Okay, so we almost know what f is. We know f within some function of y. All right, who's got the next step? How though? Am I gonna work with this one, or am I gonna work with that one? Okay, I'm gonna take that one and do what with it? Take derivative of that with respect to y. So I'm going to take the derivative of this with respect to y. So maybe this is a point where you just draw a little box around this. Like this is it, right? This is what we're trying to find right there. It's just we don't know what that is. So the next piece of this is just going to try and find that. So the partial with respect to y. All right, which is x squared plus g prime y, or g subscript y, the partial of g with respect to y. Yeah, so that means if we take this now and match it up, this has to match this. So therefore, that has to be equal to this, which means 0 equals partial g with respect to y. And now we need g, not partial g with respect to y. So yeah, integrate, right? We're going to integrate both sides. So integrate 0 dy. And then integrate partial g with respect to y. And this will give us on this side our g function. And then this right here has got to be a constant. And so we have a whole bunch of things that it could be, right? This is a constant. So if we just erase that right there, that would work. That's a potential function, right? Any questions? Okay, let's use what we just have learned. Take a look at this one. I shouldn't have erased that. Oh well. All right, it says, hey, check it out, everyone. We have this vector field, okay? Let's act like we have not done any problems today, like this is the first kind of one that we've done. Here's the vector field. We want to find the work, right, done by this field as we move along the curve C, where C is given to us by this curve right here, all right? So we could do what we did last class, and we could, you know, use the formula, right? Take the field, evaluate it at the curve. We could find dr, which is the derivative of that thing, and we could do all that, right? But is there another way? Yeah, because f is conservative, right? In that, we would check, is it conservative? That's the previous example. We did check it was conservative. Since that's conservative, we would find its potential function, which we just did. So what is little f of xy? I erased it. It was right there. What was it?
X squared y.
It was x squared y. I thought there was an x in there. No?
Yeah, the x and then the negative x later cancel.
Oh, okay. Oh, got you. Yeah, they do. So just plus x natural log x? And that was it, right? Plus c. Now I'm going to use just this one, right? So I'm going to let c be 0. All right. So this is it, right? This is a potential function. So why do I want the potential function? What's the value of having the potential function? Yeah, all we need now is to use the fact that the fundamental theorem of line integrals says that this is equal to the scalar function evaluated at the two endpoints. Right? That's all it is. And the reason we can use this is because we know that this vector field is the gradient of that scalar function. So we do need the two endpoints, don't we? So we want f at, let's see, r of 2 minus f of at r of 1. So this is f. What's r of 2? What happens when we plug 2 into that thing? We get the vector 5, 4. And then minus, we plug in 1, we get the vector 2, 3. Everyone understand what I'm doing? And now what happens when you plug this vector into the scalar function? This is just your x and y, right? That's your x and y. So here we can, now we can use this function. Now this thing comes into play, right? So this will be equal to, let's see, 5 squared, I'll do it all written out. 5 squared times 4 plus 5 natural log 5 minus 2 squared times 3 plus 2 natural log 2. Y'all agree with that? Okay, so this is going to be 100 plus natural log of 5 to the 5th minus, what's that, 412, natural log of 2 to the 2nd, right? Wait, hold on, I forgot to put minus in there. Just using some properties of logs here, and then that's 88 plus natural log of 5 to the 5th over 2 squared. So subtraction of two logs is the same as division inside one. And there you go, that's it. Okay, so we have an alternative way to do these work integrals. It requires us checking for conservative vector field, and it requires us finding the potential function, which can be a little bit of a mess. But one could argue that this work was easier than had we just done it, using this stuff from last class. Yes?
Just take away the constant of plus c.
Yeah, just use 0. Because remember, here's why it wouldn't matter. If you say plus c here, right? Then in this step right here, when you plug in right here, you're going to have plus c here and plus c here. And they're always going to cancel each other out, which is why definite integrals, when you have like limits of integration, the constant doesn't matter anymore because it always wipes itself out. All right. What we have not seen, okay, is what it takes to show that a three-dimensional vector field is conservative. We don't have a way of doing that yet. We can only use this if it's a two-dimensional vector field. However, we will have a way, not yet, we will have a way, but we can still try and find a potential function of a three-dimensional vector field. So if someone gives you a vector field that's three-dimensional and asks you to find the potential function, you can at least go after it, all right? Right now, we don't know if it's conservative, so we don't know if there is a little f or not. Don't know. But we can still go try and find it, and we're going to use the same process, but it's going to be more complicated. All right, so what would be our first step here? We're assuming that this is the partial of little f with respect to x. We're assuming the second component is the partial of little f with respect to y. And we're assuming that the third component then would be the partial of little f with respect to z, right? So you see there's more work to be done.
Yeah.
So we start with the first piece. We know that the partial of little f with respect to x must be 2xz plus y squared. Okay. So remember, we don't know if f is conservative. Conservative, no idea. All right, we have no idea. But we're going to see if we can find little f. If we can, then we can say it's conservative. All right, so we start here, matching this up, and now we integrate with respect to x.
I thought it was 2y.
What's 2y?
We're just, don't we integrate? Oh wait, never mind.
Oh, are you thinking this? Yeah. That's why it starts to get real, you start mixing things up. So just, yeah, you got to be careful. Okay, so I'm going to integrate with respect to x, right? So when I integrate the left side with I'll just do it here. Integrate the left side with respect to x, and integrate the right side with respect to x. All right, left side's just little f. Right side, who's my new volunteer for the right side? You've got to be new, though. Who's not helped today? Dun, 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 dun. Please don't speak over each other. One volunteer at a time, please. Yeah, go ahead.
So you're just integrating the function 2x
With respect to x. Yeah.
x squared z
X squared z plus y squared. Remember, treating this like a constant, so when you antiderivative y squared x, right? But remember, we have to think about what this could be, right? And this is going to be different because not only could it have constants and y's in it, but it could also have z's in it, right? So you make this a function of two variables, possibly, right? So we'll call it g of yz. As long as it doesn't have x's in it, then this works, okay? Now, the next part of the procedure would be differentiate this with respect to y and make it match with that, right? Okay, so let's now take the partial of f with respect to y, which will be, who's next? Who's up? Who's up?